Good afternoon, everyone. I'm very happy that we inaugurate a new speaker series, a new seminar series today. And it is really all about data analytics. I don't know if all of you are aware that we have a new master level program on the books, which is Master Program in Data Analytics. It's been approved by New York State and will start in summer of 18. There was a large amount of work done by a committee that was charged with development of this program, and I think we came up with a really nice curriculum, and I hope that our students in particular will consider it as they think about their graduate studies. It's a really attractive option, and I think we have a lot of really expertise and a lot of interesting ideas here on campus, and hopefully it will also bring both professors and students from different fields, in particular mathematics, statistics, computer science, business, together. But it's not just about that. As everyone is well aware of, data is everywhere. Data is around us, and data-driven decisions are made in pretty much any discipline right now. Okay, so I encourage the students to think about data analytics, and in the meanwhile, the interest will hopefully be further advanced and generated by this seminar series. We have a long-standing mathematics seminar in our department, and we're grateful that the seminar has agreed to host, if you wish, the data analytics seminar, at least initially. We don't know if the time for data analytics series will always be will always coincide, or will be always within the mathematics seminar kind of framework, but at least initially it probably will. Okay, if anyone has more of questions, suggestions, ideas, we welcome all of those, and there will be a web page that Dr. Khan created. It will be up soon, and you will be able to learn more, which we strongly encourage everyone, and we actually would be happy to bring more people really who are interested in the topic, and kind of talk and entertain these different ideas. In the meanwhile, well, today is our first presentation in this series, and it's very fitting that Dr. Sheets is our really first speaker, because he was the person who really put all the ideas that the committee developed together, and kind of wrote it on paper that later became a proposal submitted to the academic programming board, and that's how it all started. I know Dave from many years ago, and actually today is a very good day for both of us, because there were some less successful attempts of doing something in the past, like we developed programs in computational science and operations research, and it never took off the ground. But this seems to really, now hopefully it will develop into something bigger for the college. Dr. Sheets is not just a distinguished professor here who has been chair of the physics department for many years, but he also is truly an interdisciplinary researcher and the researcher in data sciences. He authored over 90 publications, including a book on shapes in the statistics of shape, and his publications appeared in journals of physics, entomology, geology, anthropology, forensics, and biology. So his interests really have been reflected in kind of many different ways and publications in many fields. But actually the central kind of idea or the thread that combines all of that, at least in my mind, okay, as far is that he uses statistical modeling and the statistics that and data science really that is behind all of that. So without much further ado, Dave, yours.
Thank you, Leonid. So it's a tremendous introduction, and Leonid is exactly right, because a lot of what runs through all the stuff that I do is all about statistical model and then the accompanying computation, right? So two aspects of that: statistics and computer science or computational science. And those are two of the parts of really what we think of as data analytics. Data analytics always has three pieces: it has statistics, it has computation, and then it has a domain, right? And so typically a lot of the domains that are coming in our program is going to be the domain of business, right? So it's business applications of these ideas. The talk I'm going to give you today is in a scientific domain, right? And that, in this case, it's geology. We'll talk about, we'll see as this develops. But one thing I want to say right up front is that I'm going to talk a lot about a lot of computational ideas, a lot of statistical ideas that have a lot of other uses. And the technology that I'm talking about here, this thing that we're calling the Chronology engine, may well have some other applications. I'm sure it does in a number of different fields other than the ones I've used it on. There may be business applications. If somebody spots that, let me know, right? Or talk to your colleagues, because we've got code to do this, right? So it's all up and running. If we find the other problems, we just kind of port it over, right? And that's true. That's one of the beautiful things about math, right? You can always find another application or another description from the world that ties to that math, and so then you already have the solution. So if you see that, if somebody realizes, hey, wait a minute, I know that problem from a different domain or a different field, talk to me about it. I'm interested in that a lot. Okay, so I want to give some thanks here to some of the other people who are involved with it, including a number of Canisius undergrads who worked on this thing. Colleen Lands was sort of one of the starting people who worked on some of these ideas with me. Colleen is a physics professor at Ithaca College. John Willis, he wrote the first version of this program. It was actually written by John, working for me. And he is somewhere in the tail end of an applied math PhD program, so some cool things. And then there's some of my other collaborators, often at UB, but a couple other places scattered around. Like most data analytics, this is not a solo effort. Usually you don't see a single person doing data analytics, it's always a team, right? So these are the rest of the members of my team. Some of these people, the Canisius students, for example, are physics or mathematics or computer science orientation. Most of the rest of the people on this are paleontologists, so a mixed team. So what am I after today? I want to talk about how we can use mathematical and computational approaches to understand events in Earth history. So that's the goal of this work that I'll be showing you now, has been that. Particularly what we're interested in is timing of events in the far distant past. How well do we understand what the events were in Earth history? This has some real implications in when we think about climate change and we think about pending extinctions. We really like to know how that happened in the past. How quickly did it occur, particularly? And what can we say about the timing of those events? Because it has a lot of bearing on the world around us now. So that's the fundamental goal of a lot of the work here. I'm looking for students to work on this. I'm kind of I'm at a point where I'm expanding some of the work. We've got some exciting things going on. I'll talk about it a little bit later. I am looking for students to work on this. If you're interested, let me know on any end of it. And then I'm also very interested to see if anybody has any other idea about how we might apply this methodology. When you switch fields, the terminology always changes. So what we think of here as stratigraphy, that's what this field is called within geology. But in other places, we might be talking about estimations of timelines. We might talk about sequences, a technology called seriation, ordination. So these things have applications in other places, and the language may differ. So one of the problems you have in thinking about methods is, how do I understand what the language is in the other field, right? We're all specialized. Scientists tend to specialize. Business people specialize. So how do you talk across fields? So I'll try to mention that a little bit. A lot of our understanding of the world particularly in the large-scale historical aspects of it, really, I think, are tied to big data in a way. Okay, this is a curve called the Sepkoski curve. This is a guy named Jack Sepkoski. He worked at the University of Rochester in the early 80s. Sepkoski started to form large-scale databases of fossils, right? Nobody had really done this before. There are all these museum collections, and paleontologists would go out and collect and report on these things. Sepkoski, he kind of got mocked for it in some ways because he spent all of his time in the library digging up information, entering it all into a giant database. But he was maybe the first person in paleontology to do that. And one of the things that Sepkoski realized, he did this plot in 1982, and this looked at the number of families of marine species. So families are one of those biological hierarchies, ways of organizing things. And he plotted these things out over geological time. And we see an Earth growth here in the Ordovician, Cambrian, sort of early appearance of life. And then we see a number of these severe dips, a total of about 5 of them in the Sepkoski curve. If you look at a current curve and what we think about these plots today, we'd find there's probably another one down in here. There's probably another big loss down here in the Cambrian, and we may well have another one going on right now. And so these are the mass extinctions, right? Large extinction losses. Extinctions were known before Sepkoski compiled his large databases. That was known. We knew about the extinction of the dinosaurs here, right, in the KT extinction, and we had some ideas about the Permian extinction. This is the horrendously large one right here. This is high levels of biological organization. The loss here was about 80% of species, somewhere on that kind of range. This is a huge extinction here. But Sepkoski showed that there were a number of other ones, right? So this is the result of sort of compiling and looking at large databases. And so that's fairly recent history, 1982, at least for me. Maybe not for everybody in the room, but I mean, that's recent history. So there's a lot to be learned by looking at these large-scale databases. I and my colleagues are working on what I would refer to as second-generation paleontological databases. There's a higher and higher resolution databases being developed. The Chinese have an immense effort at this. They've got a database of everything ever found in China, so they're really tearing along. Anyway, so just an overview of what we're going to do. We're going to talk about what a geological timeline is, show you some examples of that, talk about what that means. How are these things assembled? What does the data look like, right? It's a little bit of the background of how data is collected, how it's worked with. I'll talk about some other types of approaches to timeline estimation. Where else do we see this problem? Again, I'm interested in where that is. It may be that somebody has the same problem and they have a better answer than I do, in which case I'm going to be really thrilled, right? I've done a lot of work so far, but if somebody has a really cool answer, I'll be glad to see that. We have a set of software and mathematical ideas that collectively we're referring to as a chronology engine. So it's an underlying way of doing this type of timeline formation, and then some tools to display quality of timelines and to talk about where errors might be. So it's an associated set of methods. I'll talk a lot about my favorite mass extinction, which occurred in the late Ordovician, about 450 million years ago. And we'll talk about that. I'll show you some examples. And we'll talk about how we form these solutions, and we'll look at a case study that shows some estimates of solution quality. One of the things we get out of these solutions is not just a timeline, but some ability to say, this is where we think the quality is good, this is where we think the quality is bad. And we can start to do some interesting experiments numerically with that. And then I'll talk a little bit about approaches to some large problems, because if we want to do all of Earth history, this is a really big problem. And so we're starting to have to talk about problem segmentation, about employing boundary conditions, something we've just realized is possible, and starting to talk about parallel processing to allow us to go after really big problems. So we're starting to work on all these things. Okay, so this is a kind of a cartoon of a timeline of Earth history, right? So this is the general idea. So this idea is also known as geochronology, chronostratigraphy, stratigraphy, or biostratigraphy. It's all words that mean the same thing. It's simply talking about the ordering, right, of the history of the Earth, particularly the history of life on Earth, right, that appeared at something like, well, this is a dated, kind of poor quality example. It's a cartoon-like example. There are a number of things wrong with this. The sort of large-scale life probably appeared more like 700 million years ago now. We think that's farther back. But there's a bunch of things wrong with this plot. It has a lot of the features of what humans typically tend to think about, right? In that the dinosaurs here have a lot of space, right? If you look at the time scale, this is not uniform. It's a very non-uniform time scale. We're emphasizing terrestrial, big, cool animals, right? When actually the really interesting stuff is going on out here in the ocean. That's where we got lots of data. So the data I'm going to be showing you is not on land, right? We got all the cool fossils, but out in the oceans where we got invertebrates that die in huge numbers and leave a good record, right? So the cool stuff is out in the oceans, not on land. And that's something we also tend to forget a lot when we think about our Earth, right? Most of it is the ocean. So the cool stuff is actually going on out in the ocean, not on land. But this plot emphasizes land. But it's a cartoon or a child's version of this sort of thing. Okay. But that's what we're trying to produce. I'll show you professional versions of that. We'll go into that in more detail in a moment. So what other problems are similar? So one term is seriation. So in fields like archaeology and anthropology, there's a lot of interest in ordering, particularly things like grave goods or pottery remnants. And you can do this by ordering or sequencing the patterns of decoration on them. And so you can talk about the artistic evolution or the stylistic evolution of grave goods or other recovered anthropological ideas, and that's called seriation. A method called sequence ordination appears in things like operations research and control theory. May be able to describe supply networks, for example, in business settings. If anybody has more detail on that, let me know. There's a method within geology called sequence slotting, and this is an attempt to merge univariate, temporally ordered data. So this crops up in parts of geology on certain types of data logging. Matrix sequencing, this is often crops up in things like within operations research and some other areas where you're trying to optimize an ordering or structure of a matrix. And that's sort of similar to what we're doing. Ordering of matrices can also be used as a data visualization in complex systems, looking for patterns or clustering or structure in large data sets. So there's some other related uses here. What we have is a little different, but in a lot of ways will let us do any of these operations. So the techniques I'm going to show you will do all of this at the same, so you just change the data type, change how it runs a little bit, you can take on any of these different tasks. So we think we have a very highly general sort of solution. Within geology, this process of forming timelines goes by a lot of different names that often depends on what type of data you're using. The predominant method has been historically is what we call biostratigraphy, just keeping track of the coming and going of different species. What species were present when did they arrive, when did they leave the Earth. You can also do lithostratigraphy, that's ordering by rock structure. Chemostratigraphy, this is ordering via chemical evidence. So we'll see that a little bit later. We've got some ocean chemistry data we'll make use of. Magnetostratigraphy, ordering by the orientation of the Earth's magnetic field. Earth's magnetic field reverses periodically, and you can order things based on that information. And then radioisotopes. So when you're very lucky, you have some radioisotopic dating from atomic radioactive decay of materials. So these are thought of as separate fields. One of the things that we do with the chronology engine is we can work with all of this data simultaneously, and that's one of the strengths of the method. So we can mix different data types. That lets us carry out a lot of interesting hypotheses about whether different types of data agree with each other. So some interesting things we can do there. Okay, so this is the current thinking about Earth history. So this is put out by a group called the International Commission on Stratigraphy. This is the current official kind of international idea of what the sequence of events in Earth history looked like. So this is the entirety of Earth, right? And the Cambrian, right, the pre-Cambrian era, we started to have the Paleoproterozoic back in here. We started to have some large-scale life appearing well back into that. So there's some cool things going on. The era we're interested in is the Ordovician, and that's located right in here. So this is the location of the Ordovician mass extinction. That's the thing we're interested in. This thing gets updated about every 4 years. There's a new update of this. The general structure of this stays pretty much the same over time, although some of these dates along the time of some of these intervals in here changed by as much as 4 million years in the last version of this. So there's still quite a bit going on here. This is not a completely locked down and solved science. It's very much evolving. This is a zoom in on the Ordovician time scale. It's got a series of names on here. So this is the time axis along this side. It's divided up into the lower Ordovician, the middle, and the upper. And then there's a series of names that are associated with this. And this comes out of the cultural traditions of different parts of the world. We're collecting data from across the globe, right, to do this. And we've got different names and different local traditions about how they talked about the geology. So when you're dealing with this, you have to think about the correspondence of different parts of the world when you do this. So that there is some real severe data management issues in all of this that we get into there. The other thing that's visible on here are what are called GSSPs, which are global section stratotype and point. These are collections of data that the Commission has agreed on are markers in time. So these are specific locations on the Earth. They have specific characteristics. And these particular locations are thought of as marker points. So they're scattered through here at all the boundaries. And so everything is related to those marker points. And that's how we really tell where we are in time, is where are we relative to what's happening at these GSSPs or marker points. So part of what we'll talk about a little bit later is assessing quality of GSSPs. We can use the technology we have to try to decide if a GSP is a good quality. these things, if you notice, they're located at different points around the globe. And I've been in some meetings where people have talked about this, and there's a lot of nationalism involved in which things are GSSPs. There's a lot of national pride going on here. And so, really what matters with the GSSP is how well you can relate it to other information, how connected it is to other data. And we have some ways of talking about that. Okay. So how are timelines formed? We collect up a lot of data from different locations. We refer to a location as a section. It's a geological term. It means a location on Earth where we got a whole stack of exposed rock we can take measurements from. We're going to compile all this information from many locations around the globe into what's called a composite section. So we're going to merge them all together and get a single timeline that spans more time than any individual collection. So we've got these localized sites we're calling sections. Within the sections, there are a series of horizons. Geological data is ordered, so it's stacked up on top of each other. So these horizons are ordered within its sections. So we've got this local information about which events occurred when. And what we're going to do is connect that all together to figure out what the overall time scale must have looked like. A section might be anywhere from one horizon, so there's no real internal ordering, up to some that are into the hundreds of horizons. We've got some data from parts of Eastern Europe that have hundreds, up in the 800 to 1,000 collections within a single locality, right? So some really exhaustive work has gone into these things. Most of these things are exposed rock faces, so the paleontologist can go out and collect the material there. The others are drill cores, right? So they've been sampled drill cores that have been drilled into the earth. So this is a section. This is one of the GSSPs in Zhejiang, China. Paul, you can do better on the pronunciation of that than I can. So this is an exposed section. So we're talking about sections of rock. China has got these beautiful, long, exposed sections of rock on some of the hillsides in parts of China, and they have these fantastic data collections there. So this is something that's appeared since the early 80s. Chinese paleontology really kind of lit up in the early 80s. And then on these maps, you can actually look at these rock sections, and they can identify specific events that occur at particular locations across those sections. So that's what the actual data looks like in the raw. It's typically reported like this. You're not going to be able to read this chart because it's too fine a level. But what we're seeing on this side, this is a time axis. So this is the lowest times. There's the upper times at the top. It's also rock height. Right? So these are the lowest levels that buried the deepest. And then as we move upward, we're moving upward both in rock and in time as we go across that hillside. This is a listing of every single species that was found at this locality. So they've got this giant listing of what was present. And then they've got divisions. They've got collection numbers here. So these are individual. So when I say horizon, I'm talking about an individual collection like this one. The Chinese put this in little bundles, and there's differences in how people in different parts of the world collect data. But nonetheless, we're thinking of these as horizons, single collections. And so for each single collection, there's a dashed line if the species is not seen there, and a solid line if it is. So we've got this record of presence and absence of species through time at each locality. And so that's what the raw data looks like. Okay. So this type of data is very noisy, it's incomplete, and the sections contradict each other. And so these are kind of not uncommon to a lot of data analytic problems, right? Your data is never as good as you'd like. Sometimes this is severe enough to contradict, and it's always noisy. Hiatuses, for example, are common, right? There's a whole section of time that may be missing from some of these records. It looked like we had a nice continuous plot, but if there's no rock deposit, if no sediment develops during an era, what happens? You got no record of that time, and it may not even be obvious, right? You just may be missing some information, and you're not going to be aware of it from looking at the material. Sometimes the geologist can tell you that. Oh, we think we got a hiatus right here. No idea how big it is. We think we missed something. Other times they can't tell that. We tend to think of locations on the globe as having a specific ecology, right? If you go out in the woods, it's going to look like that tomorrow. It looks the same. But over geological timescales, the environment moves around across the globe, right? Conditions are not the same over time at each location. Water gets thick, deeper, shallower. Other conditions change. So that even though the location may stay the same, the organisms living there may shift. They may move around on the surface of the globe kind of underneath this. And so that means we're going to get missing information at different times. We're not going to get a continuous record anywhere. One of the things that really drives me nuts, from the point of view of just being an applied math person, in that there's a tremendous amount of human error in this. And sometimes when you get results, usually when you make a mistake in a result, you show the result back to a paleontologist and they're like, that can't be right. This thing is in the wrong place, right? They can tell you that from intuition. But sometimes you come back with a result and one of their species is really in the wrong place. And what happens is they all go back and they look at that species, and they go back to the museum files, and they all look at it, and they put their heads together, and they talk about it. And after a while, they decide that one of your data points is not what you thought it was. So in the middle of the project, they rename data points on you. Stop and think about that one, right? If the data gets renamed as part of your process. So you have to, there's a lot of data management that goes on here, and keeping track of, okay, who got renamed when, keep track of all that. Even the radioisotope data, and that's the gold standard, that's the best we've got, has a certain amount of error associated with it, both in the collection and then the processing and then the physical measurements involved in dating radioactive dates. So there's a lot of uncertainty of different types in all of these problems. Okay, so how do we deal with this? We've got data which is structured in horizons, so that's the fundamental piece of data here. So a data is a horizon is a listing of all the information we have at a particular slice of rock, right? It could be, it's often this presence or absence of specific species, but it might be other types of information. We might have information about what types of rock were there. We may have radioisotope dates. We may have some chemical statements, right, about the ocean chemistry that was going on at the time. We might have paleomagnetic data, but it's whatever information we have. And this method was meant to be very flexible in terms of the type of information we can work with. So basically anything we collect in a single stripe of time, we can insert into this program. So any kind of measurement we have, right? If there's more than one horizon in a given section, we might have a case where we just got one little slab of rock that has interesting, cool stuff on it, and we want to work with that. Hopefully what we got is many layers at a given location. But even if we only have one, we can still work with it. And we do have this temporal ordering, because if the collections are in rock, we know what the local order was, right? We don't know the global ordering of events, but we know that Horizon 1 is below Horizon 2, and that's below Horizon 3, and so on. So we've got some information. So we can put this into a matrix, like an Excel file, with each horizon having a single row of the matrix, right? And then the columns represent different types of data, and we can record whatever we want to on rows of the matrix. So a real common representation of data. You've all seen this in things like Excel. Then the chronology engine searched for an optimal ordering of all this information, right? So we're looking for the optimal way of structuring this. If we had, we know we have all these disagreements, right? So we've got all that going on. We've got noisy data. We've got contradictory data. If we're really lucky, we might have a statistical model of what those errors look like, right? In a lot of statistics, you have a model of what error looks like, and then you can use that error to do an optimal order, like a regression model, right? Here, we don't have that. This is too complex a system to easily say what the errors would look like. But we can define what's called a penalty function, sometimes an error or objective function, because we can say, in a good solution, this is what should happen. This is what a good solution should look like. And so we can define errors depending on what the data is. We can change the error. We use different error functions. And then we can try to optimize that. So this is an optimization of a penalty or objective function. This is a very common way of optimizing events in data analytics, right? There are different types of optimizations you can carry on. But with biostratigraphic data for the moment, the penalty function we use is the number of unobserved occurrences or the total duration of all fossil species. We think the best answer has the fewest kind of special pleading, right? Because if you can compact all the observances of a species closely together, you're not claiming that there's a lot of missing data, right? And that's really the criteria we're using. And we'll see a little different criteria. You can solve this thing under different types of penalty functions and different criteria, but that's what we're using at the moment. So let me show you how this works. You can actually do this in Excel. If you had a lot of patience, you could actually work out this whole system in Excel. It would be a horrible experience, but you could do it. So this is what a section record looks like, okay? So what we've done is assign a score. We assign the scores initially at random so that the lowest sections, right? So Horizon 1 has the lowest score, and then the highest numbered horizon have the higher scores, right? So they're ordered temporally. And we do this for each section. We sort of randomly start out by assigning these ordering scores to each collection of data. We got a little bookkeeping here. We keep track of which section and which horizon we're talking about. And then we got a series of data. And so here, the A, B, and C refer to species. So these are some fossil species. Doesn't matter what the names are, right? A, B, and C. And we put a 0 if it's absent and a 1 if it's present. If we never see it at all at that location, we put in an X. Because there's a little bit of difference between seeing the species sometimes and never seeing it at all. Right? Because if you never see it at all, it may simply be the wrong environment, right? So it's not that it's missing, it's that the location is wrong. So anyway, we can talk about that. We have a thing in here called a marker bed. Now, a marker bed is a chemically matched piece of rock. And so we know, for example, in the example we'll see later, that we've got two sections that share a common marker bed. And so those things ought to be right next to each other in the solution, right? About that? It's the same deposition. We also have some ocean chemistry information that we refer to as the isotope rise and the isotope fall. I won't go into all that, but it's a way of talking about what's happening to ocean chemistry. And if you think about it, if there's a trend in the ocean chemistry where it rises at some points and falls at others, what's got to be true about all the rises? They should be before any falls, right? So if we're ordering the data in time, sections that have indications of rising ocean chemistry should always be before falls. So we take these randomly assigned scores and we merge them and we sort by this score column. And then we look at each column and we say, okay, how good was this particular ordering of the data? It started out at random, so it's going to be bad, right? Just started at random. So for example, on species A, we got some zeros in here. So what does that mean? If there's a zero within the range of the species, it was alive then, but we missed it, right? It didn't appear in the data set. And so that's a missing data in there, and we think of that as an error. So there's 3 missing data points. Oops, I've only got a 2 there, I got an error. But those are missing data points. Look at this marker bed. What's the problem? Were the 2 marker beds adjacent? No, there was something else in between them. We think these 2 marker beds are the same thing. So they really ought to be side by side. So what we can do, and then here, the isotope, it looks like we got all the rises coming before all the falls, so that looks good. So when we count up the error here, I should have had a 3 instead of a 2 here, because we got 3 of these zeros in the middle of the species range, so there's missing information there. And then here, we got a 0 in between the marker beds. We think that's a much more important error. We gave it a high score. So in other words, we're counting each of these, and then we're counting the zeros here, multiplying by 100. So we've got a large error for this particular arrangement. Okay, so that's what the data structure looks like. That's what the initial setup looks like. The algorithm we use to work with this is called simulated annealing. It's a way of looking at finding an optimal solution for a system. If you have a penalty function, you have a way of rearranging your data, you can do this. So what we did, we assigned these initial random scores, we calculated the error, and we saved that information, right? Just like I showed you a moment ago. We then generate a proposed solution based on the current solution and compute the error. So what we do is we take that observed solution and we alter one of the horizons. We move it up, we move it down, we stretch it, we compress it, we split it. We do something, right? We alter the scores of one of those sections. And then we look at that. If the error after that alteration is better than the best solution, we store that, right? That's a best solution, go back and keep looking for more. If the error is less than equal to that of the current solution, if that's true, we'll use this as our proposed solution and keep looking. If the error is greater, sometimes we look at something called a Boltzmann factor, and we use this is a randomization. So this algorithm sometimes takes a solution that's worse than what we started with. Because if you're greedy and you go downhill toward a solution, you can hang up, you can get stuck. You need the algorithm to be able to kind of wander around and explore what's happening a little bit. So this is a technique called simulated annealing. It's based on the techniques we use to cool down glass or metal to provide a strong structure. So that's this annealing process. So in either of these cases, if we found a reasonable solution or we've decided to accept a bad one, we keep that as a proposed solution and work from there, and we follow this process for a while. As you do this, you simply monitor the error, you watch how the error decays off over time, and eventually this will stabilize. We don't really know for sure that we're at the minimum solution, but we can be pretty sure we're at a good solution or a low penalty solution. So there's a little bit of art to this, right? It's not a pure science. Okay, so one of the important parts about this is how do we alter scores? Well, we can move a whole section up or down. So we take the scores and we add a constant to them, right? If I take one section and I add a value to all of its scores, it moves it up or down in the solution. We could insert a hiatus or a gap in a section, right? So we can take it, we can sort of randomly pick a point in the solution, right? And insert a little bit of blank space in the scores. So we like increase the scores on the upper half or the lower half of the solution. We can increase or decrease the sedimentation rate. And what that means is we rescale it, right? We sort of zoom in or out on a section of the solution. We can insert what's called a dog leg, and so we sort of postulate that part of a section sped up anyway. And we can just swap adjacent horizons. There are a bunch of moves we can make, so I'll show you what that looks like. So in this case, I added 0.4 to all the scores in section 2. So it's the same example I showed you a moment ago, except that I increased the scores of this section all by 0.4. So that meant that this whole section was moved up in time. When we do that, and we put them back together and merge the two, right? If you look at this, we have 3 gaps here, we have 1 gap here, but now we have 2 gaps between that marker bed, right? So this is inferior. This isn't as good as what we had before. So this is a bad solution, right? Okay. And so we can do that. Once we have an alteration of the scores, we can infer what the order had to be and then what the penalty is. And we just keep doing this until we find a good penalty. So here's another change. The scores in section 1 were all multiplied by 1.5. So I just took these scores that originally appeared here, multiplied them by 1.5, merged it all back into one giant matrix, and this time we got a much lower error because those marker beds moved together. Right? So the marker bed's now aligned. We've got 2 gaps in here, so we've got an error of 2, but that's a big reduction in the error. It's a better quality matrix. Okay. We can define penalties or these error functions for whatever type of data we have. If the geologist can articulate what should be happening in the data, this type of data should match, this date should be after this date, we can set that up, and from the matrix you can calculate out what the penalty would have to be. It's a little bit of imagination. Okay. So I want to show you a case study of what this looks like in practice when we start to use this. So this is from some work I did with Mike Melchin and some other friends of mine. It's published in a journal called La Faya. And it's talking about, here's one of Mike's title slides. I took this from some of his presentations, so grade me gently on this because I stole his presentation. So it's not purely my alignment on this. Okay, with his permission, right? I'm a co-author on this thing. What we're looking at here is some of these GSSPs. We're looking at them near our favorite mass extinction at the end of the Ordovician, which led into the Silurian era. And we were looking at saying, are there ways of using horizon annealing? I guess I should have mentioned, this is the original name for this method, was horizon annealing. And I'm now calling it the chronology engine because we can do a lot more with it than just align geological horizons. This was looking at the quality of these GSSPs, about saying, are these the best choice of GSSPs, or are there other choices we could make? How stable are they? How well related to other data are these particular collections? So that's some of the questions that Mike was particularly interested in. So again, so what we're looking at is, could we use something like AHA? Could we use these automated methods of looking for solutions to aid in the selection of GSSPs? And we're going to look again at this, what's called the Hernantian, the latest Ordovician, and the base of the Silurian. So these 2 particular times that we think are interesting. So part of what Mike is asking, how do we incorporate data from different types of assemblages and multiple other lines of evidence? So we're still in an exploratory process. So how do we incorporate multiple types of data? How do you get biostratigraphy? How do you get lithology? How do you do this? And when you do this, do the different types of data agree, right? Or what kind of change do you get in a solution when you incorporate more data? You know, and is the data internally consistent? So a bunch of questions like that. Could we assess these GSSPs? Could we look at a couple things that a couple collections of data that might be good GSSPs and talk about, are some of them better than others? Meaning that they're more stable? Can we look at significance of correlation hypotheses? So this is asking about ordering or synchronicity of events in the fossil record. Did these 2 things happen at the same time, or did they happen at different times? So one of the big questions about mass extinctions is how fast did it occur, right? So mass extinction, what's the nature of a mass extinction, comes down to the idea, what was the correlation of the extinction events? Did it happen at the same time everywhere, or was this spread out over time, right? Because there's a lot of implications about what might have caused the mass extinction and how that occurred. Then also with this, can we talk about what temporal resolution we have? Are there ways of using these methods to decide how fine a statement we can make about timing events, right? What's our resolution? Mike showed some results here of this HA, the chronology engine, and then an earlier program called CONUP. CONUP was really a similar type of method. CONUP orders, which is a guy named Pete Sadler and his collaborators, CONUP orders events. So it doesn't order collections, it orders the coming and going of species. So CONUP and HA are kind of related, but they come at the data from a different direction. And in some ways, so CONUP was a big inspiration for us in writing HA, but we order the data and we handle the data a little differently. And that lets us do some things that are hard to do in CONUP. So again, in his presentation, we've got this misfit, right? Misfit, another word for penalty or objective function or error. And we're minimizing that based on all the same types of data. Again, we're looking for taxon ranges, species ranges, that are compact, right? So no missing information. Both of these use simulated annealing, so searching. Okay. I'm going to skip a couple things here, they're not critical. The data set we're working with is this one. This is a collection of 27 sections, so 27 distinct sections from 4 paleocontinents. We're working with a species of planktonic organisms called graptolites. They're now extinct. I won't go into all that. But this is an Ordovician set of widespread planktic organisms. They lived floating around the water column, eating other plankton. We also had a number of isotope data and lithostratigraphic matches in here. So we have both some biology, some chemical isotopes, and some geological information. So this thing had a total of 630 horizons and 113 taxa. So not a huge matrix as far as these things go, but still, this is a lot of searching. This is a picture of the world in the Ordovician. This is the South Pole up here. There's the North Pole. The continents were all kind of clustered down in the lower region of the world. As a point of interest, I guess. There's no ice caps at this time, so there's no polar ice in this era in Earth's history. It was a very warm ocean. It was also very stagnant. And so part of what happens in this mass extinction that ends this is that there's a change in ocean circulation pattern. You start to develop ice at the poles, and the ocean habitat changes drastically. And so a lot of the plankton that we're talking about here went extinct. Right? Their lifestyle, their habitat went away, and they went extinct. It was certainly, in this case, driven by climate change and the shift from a very warm, stagnant ocean to a much more kind of vibrant ocean like the one we have now with polar ice caps. So anyway, so that's the background. Mike shows this result. This is a slightly different study. This was material from China over what's called the Yangtze platform. The two solutions here, these are range charts. It's not labeled, but these are ranges of individual species. And what we're showing here is a solution from CONOP and a solution from HA. So these are two kind of not really competing methods, but alternative methods. And what's striking about this is that the agreement is actually really high. It turns out when you look at the different methods of doing this, when they run the same way, they tend to give you pretty much the same answer, right? So there's there's some pretty good data here is what this part of what this means. One of the other things we did with this that the chronology engine lets us do is to start to introduce ocean chemistry. So this isotopic carbon excursion. They're looking at the relative density of carbon-12 and carbon-13 in shells, fossil shells, and that has to do with ocean temperature. So there's a way of looking at the isotope signature in fossils and getting some sort of estimate of what relative temperature was like. So there's this spike called the Heiss rise and fall that's in here, and we think that was global, so we can use that as a way of aligning time here. And so we have that information. We also have some of these marker beds in some of the Chinese sections, which we think these are identical pieces of rock. Okay. So this is what a solution looks like from HA. When we're done, we can pick this gradually. So the information we have here across the bottom are different sections. So these are names of different locations on the globe, right? So these are different localities. And then the individual lines on these are the placement of the horizons from these different localities in time. So this is a time axis going up here, vertically. We can place the GSSPs, because the GSSP, so Wanjiawen North has a GSP, and it is this particular horizon. So we can place that GSP in time, right, within our solution, and draw a timeline marker across here. And then this is, again, this is the boundary of the Silurian era, and that was in a place called Dublin, Scotland. Right, so we can see where those appear in time within the solution. We can also get some idea about solution density, right? How tightly packed are the solutions when we draw these types of drawings. So this is called a section range chart. It's one way of displaying data. One question you might ask is, what's the resolution of something like this? How finely can we subdivide this? So, and the other aspect is, what's the error levels in this, right? How reliable, how good is that solution, right? How tightly placed are those horizons? Okay, we don't have a statistical model of what error in this data should look like, right? We don't have a statement about what's the probability of different types of results. But one approach we can use is called Jackknife Analysis. And so this is a permutation method. Yes, Matt, you can talk about permutation methods much?
We do.
You do. So in a permutation method, what you simply do is you randomize the data itself. So you don't try to build a model of the error. You randomize the data in some way, and then you rerun the whole analysis. Okay? So we can do this. Since this is all computerized, we can randomize, and we use something called a Jackknife Analysis. This is a very simple randomization of the data. What we do is we pull one entire section out. So remove one section, rerun the whole solution. Do that over and over, removing one section at a time. So we kind of deliberately damage the data and see how much the solution moves, right? So if the solution was very high quality and I took out one section, would it matter? If there's a lot, if I've got a very rigorous solution, I got a lot of data, I pull one section out, does anything change? No, probably not. If the solution quality is very poor though, right, if it's only kind of a marginal solution, I take out one piece of data, what happens? We see a lot of changes or a lot of degradation in the solution from the data loss, right? So this is a very simple model, but instead of trying to statistically think about the error or what's wrong, we're permuting the input data. And then we have to run the whole solution again. So this is time consuming, right? But you can do it. When we do this, then we do this many times. We take out one section at a time, remove them all. We get a little bit of variation in this, right? So well-constrained horizons show less variation than poorly constrained ones when we do this. And we can measure this, right? You keep track of where everything winds up in each of these solutions. You do it many times. You get a distribution over these jackknives, right? So over the repeated operations, you get a variation or variability in each solution point and in things like the location of those GSSPs, right? They'll move around a little bit in the solution a little bit as you do this. And so we can plot that. For example, what we found out in this was, one measure of this is to take the standard deviation of these jackknife positions. And that's a way of talking about relative quality, right? Just compute the variation, standard deviation, over the data set. We can also do some things like talk about event order. And does the event order change? We'll see what I mean by that in a moment. Okay, so when we do this overall, we had about 630 horizons. This 2 sigma range, right, was about, the mean sigma was about 9.7. So in other words, when we vary the data, they move by about plus or minus 10 positions out of 600, right? So that gives us some idea of what a resolution is, right? The variability within the data tells us what the finest resolution we can claim is, right? Anything below that is within this kind of error, right? So if I added one more section, one more bit of data, that can't really change things very much, right? So there's our claimed resolution. We can also take this information and plot it, right? We can rank each location in the solution, right, as to what quartile or quintile that standard deviation was in. So well-constrained horizons here we got marked in black, and we use a false color map. So we're up to red or very poorly constrained horizons. You can do this with species as well. I won't show that, but you can do range charts of when the species came and go. And you can put this types of quality map on it. It shows something a little odd here. What's very strange about this map? What's peculiar here? Where are all the black bars? At the ends. At the ends. Is that real? It's probably not, right? It's probably not real. The black bars always wind up at the end. In this trial, and in prior trials of this, we haven't been incorporating boundary conditions. And I realized, within the last couple of weeks, that we really need to start including some boundary information. We've got boundary information on the problem. What happened before our data, what happened after our data, right? That's a boundary condition. We could incorporate that. Because at the edge of the solutions, we don't know what the boundary is, and the data gets sparse. So when you have sparse data and you're trying to organize sparse data, you really don't know much about this, but it falls in the same spot every time. There isn't a lot of options. When the data is very dense, probably in this middle region here, right? These things are moving around among themselves a lot because the data is so dense. We don't have a lot of information about where they go really, but we got a lot of data, so they're all kind of this jumble in the middle. So we've got what are called boundary effects. So this plot is not purely boundary effects, but the upper and lower edge are. So the edges of the solution kind of degrade because we're at the end of this. As I said, we've come up with the idea of using boundary conditions. We think we're going to be able to improve that, but that's another story. Okay. So this is saying we think that these two regions, these banded regions at the end, are not trustable. You can't really trust this. So if you really want to know what's happening in this region, we need a lot more data below it to take care of this kind of artifact of the boundaries. One of the other questions we had was whether or not this resolution, right, the 2 sigma range, varied throughout the solution. So this is a plot of the standard deviation, right, over those jackknives as we move through the solution, right? So we've got the boundary ends where the sigma is small, those artifacts, but sigma is not uniform throughout the collection, right? We've got some regions here of high uncertainty, right, in the temporal ordering. And we got a region here of relatively low uncertainty. So we can map out where the solution is good, right, meaning stable, and where the solution is not so good. So that would be some guidelines to say, here we trust this ordering, and these are regions where we don't trust it. So it's some statements about kind of belief, I guess, in the quality of the solution. The 2 lines that are shown on here shows something else. We can run this solution with different types of information. So we can run the calculation repeatedly. This upper one included only the biological information, the coming and going of species. This lower one included the lithological information about marker beds, and it included that isotope data. So what's immediately obvious when you include more information? What happened to the solution? It got more stable, right? There are lower sigma values when you include more. It's better stabilized by the addition of more information. And so you can see things like that, right? You can measure these things and plot them. We did this. This is what's called a moving window average. So we sort of took a little slice and moved it along and looked at the average resolution within each slice. So we can make statements like that. This is handy, right? Because if we wanted to improve this, where should we be trying to find more data? Where is it important to find more data? Here and here, right? Those are the regions that have poor resolution. So that's where we want to look maybe for isotope data, right? If we get isotope data, we can stabilize that a little more. Okay. So one of the other things that Mike is interested in is, do these different GSSPs have different stability, right? Because the GSSPs are supposed to be markers in time. So if they're good markers, they'll be in a stable location in our solution. And we can look things like that up. This is, again, this moving window average of all sections. And these are some candidate GSSP sections. For example, this is the current, what's called the Hernantian GSSP. That's a location in China. So there's that particular point. There's its error level relative to the average. Okay, that's good, right? There's another alternative here, though, this other section, at a location called Vanini Creek in the US, that's actually slightly more stable. Not much more stable, but slightly, right? So a little bit of difference. This is the boundary of the Silurian era, right? And noticeably, it's a very stable location. So somebody did a good job of picking this particular marker, right, for the end of the Silurian. This particular GSSP is a good quality one. So we got some sort of criteria we can talk about whether or not one section is a good or a bad GSSP, at least in one way of thinking about it. You can show things like the resolution of these boundaries. These are the GSSPs. The width of that little fuzzy boundary is its 2 sigma band, right? So we can talk about how clearly do we know what the boundaries are, right? And so obviously if we want to talk about this mass extinction, we need to squeeze that boundary down nice and tight so we got a really good idea of exactly when the mass extinction did occur. We can look at the simultaneity of events. So when we look at the appearance of, in this case, a particular species of plankton, right? It first appeared. We can look at the first appearance at different locations across the globe. So again, this is the timeline across the bottom. The marks here are the observation of that particular species at different locations. And so, for example, this thing is thought to have appeared sometime after the mass extinction. This thing was a recovery taxa in the aftermath of the mass extinction. So Dobbs-Lynn is a GSSP, and there's one of the early appearances of this particular species. But it showed up in China earlier than that, right? So this Chinese section, either that species was present in China, or this is a bad placement, I don't know which, but it showed up there. And at some other locations, this species appears at slightly later times. So we can talk about when does the species appear, is it synchronous across the globe, or is it different times? We can take that plot, and we can use things like t-tests. So we can look for significant differences in timing. And it turns out that, remember, we had a resolution to this system. And the appearance here in this Chinese collection is not really significantly different from when it appeared at Dobbs-Lynn. This looks a little earlier, but it's within the error bounds that we have in this system. So we could say, well, I'm not really worried about that because the difference in the appearance time is within my error range, right? On the other hand, some of these other things here, like Fanjiang, this is really significantly different. This first appearance was later. So we can say that at this particular locality, this species appeared a little bit later than it did here. And so we can make those types of statements. So that's geologically interesting. We can talk about, are 2 events at different locations on the globe synchronous or not, right? That's what you'd like to know about things like that. Okay, I'm going to skip ahead here a little bit. Oh, well, temporal resolution. Let me mention this. So we looked at some temporal resolution in this system. We had this mean sigma of about 20 in this. The study interval we're looking at here is within the valid region, about 450 of them. The duration of this whole thing was about 3.6 million years. So our resolution here is about 160,000 years. So that's what each slice, that's the resolution we can achieve here. That doesn't sound great until you realize this whole thing was 450 million years ago, right? So this is way back in Earth history. So we can make statements like this, right? From this, we can actually say, here's the achievable resolution given the amount of data we had. So if we have more information, we could tighten this up a little more. Okay. So this was Mike's statement of what we can get out of this, right? We can get some measure of these quality of GSSPs. We can get a range of error uncertainty in the location of these things. We can talk about the diachronaty, simultaneous nature or not, of some of these types of events. And we can look at temporal resolution in this. Okay, this is Mike's slide acknowledging a lot of the contributors to this. We had funding from NSF and a bunch of other things. National Science Foundation of China. This is the Canadian National Sciences Foundation. Okay, so at the moment, what I'm interested in working on is using parallel processing approaches to large data sets, right? This is an NP-hard problem. I don't know if you've heard that term. It means non-polynomial hard, which means that as the data sets get larger, the solution times are exponentially increasing. So it's larger than any polynomial function. So in other words, if you double the solution, it isn't 4 times as long or 8 times as long. It's something much worse than that, right? This thing gets much, much harder to solve as the solutions get larger. So one of the things we're looking at is how do we segment the data? There are ways of splitting these things up into smaller problems and looking for local solutions within smaller pieces. We think that we can use boundary conditions. Geologists know more than is in the data set. They know about what happened to species before your data and after your data. So we can make some statements about what was happening on the boundaries of these data sets. And we think that's going to help clean up some of the results. When we segment things, we also need to know about boundaries. So there's some interesting computational problems there. There's some other types of approaches to looking at error uncertainty. There are a bunch of other resampling methods we could try. We just haven't done it to date. There's some approaches to things called sensitivity studies. We have looked at a little bit of that. I won't go into that unless somebody really wants to talk about sensitivity in models. But and then the other thing I really wanted to bring up is the idea of possible other applications. Because this system will order any type of data, right? It doesn't care what it is. If we can write the data down as lines in an Excel matrix, you can order it, right? This will be a way of achieving and ordering under any kind of criteria you want to name. So this is a very flexible system. And again, by looking at some of these different types of permutation approaches, you can put confidence statements on that ordering. So not only do we get an ordering, we get some statements about how good we think it is, which is, in a way, is really important. So that's what I want to talk about. So if you have questions, please ask. Yeah.
Does sensitivity include sensitivity to the scoring? Because the scoring basically is subjective.
Yeah. Yeah, the scoring is completely subjective, and then you're using the scoring, you assign the scoring at random initially, and then you kind of permute that. And then once you've done that, you look back and say, was that a good scoring or not? And you're searching for the optimization of that scoring. So you could use different types of scoring schemes, would be one possible way of thinking about this. We're just using floating point numbers, and we keep them scaled within a range. I'm going to all the computational parts, but yeah, that's another one. Sensitivity to how we permute those scores. There seems to be some operational questions about what's the optimal way to do that. The boundary condition ideas is another cool one. Yeah. Sensitivity, there's some ways of looking at how sensitive the penalty function is to locations of particular taxa, and you can track that. So there's some other ways of thinking about, there are ways of using the penalty function to try to understand how good the solution is, that looks at how sensitive is it to an individual positions of collections within the solution. Yeah, so there's some things there.
Yeah, I'm wondering if you can use this for stock market trading patterns. Maybe it's already used or something similar.
Yeah, the big thing, so they're clustering algorithms that look at the packing of similar objects. What's really different here is that there's an inherent order to them, right? So the ordering of within each kind of bundle of information matters, and that's a lot of what we're using in the solution. So we're looking for data analytic questions that have to do with ordering, right? So you have maybe in a business you might have a series of tasks that needs to be done, and you've got a whole bunch of different operations doing different tasks, and you're trying to figure out what would be the optimal way to order those tasks. So that to me is maybe the way to think about it.
Yeah,
I don't know, maybe there's something within the stock market that has an ordering component that we can look at.
Or maybe the comparison you were saying, what was the word? Measuring the quality of a pattern.
Quality of patterns, yeah. So I mean, the ideas we're using here to talk about the quality of the pattern, we permute the data, right? We do those permutation methods and use that. That applies to any optimization, right? So some of the things we're doing here, understanding how to do that, you apply it to any optimization. So You know, there's kind of a lot of generality with, to some of these ideas. So I mean, that's the thing about working on some of these. You can steal the ideas and use them on another problem. Share the ideas.
You mentioned making some random choices. What kind of random do you mean? True random or?
It's computer-generated random, so it's pseudo-random, right? And so they are, I mean, pseudo-random sequence of choices. You get pretty good algorithms for getting good pseudo-random choices, right? So it's initially it's just an ordered. We draw out of a uniform distribution to initially set the positions, and then you're permuting that. So you're searching through it with a variety of different, we call them moves, to change the scoring within each section. You look for the optimum. Yeah.
If you went to a true random number generator, if you used hardware, would that be?
You might improve matters a little bit. We tend to run these solutions more than once. So you run them several times, multiple times. We think there are a number that these problems are typically underdetermined, right? So that there's a lot in here where you really can't tell the particular ordering of all the details in this. So some of that uncertainty in the position is kind of irreducible. You're not going to ever be able to beat that because you get horizons that both have all the same species, right? So you really don't know what that means, right? You know what I mean? If you've got two collections that all share the same species, they look identical, they got the same pattern, which came first? No idea, right? It's changes that allow you to pick that out. So part of the uncertainty in this is irreducible. Yeah, and we've seen that. Some of the sets we have more data poor than others, and they're difficult to work with because you don't get a good solution quickly. Yeah. So there are multiple good solutions on these, is what I'm saying. So, so if I wind up with one of them, okay, we're probably good enough.
Yeah.
Yeah. And then we do things like change the penalty function and look and see what that does. So when you get to a final solution, you're looking at a number of iterations, really.
Basically, the idea is you do iterations until things kind of settle down in some way.
Yeah, you run this thing, you iterate this. I didn't talk about the simulated annealing idea, but basically you have what's called a temperature parameter. And at the start of the search, you allow the search algorithm to pick bad solutions. And as time goes on, you force it to only accept good ones. And so it allows you to kind of move around and try different locations within your parameter space. And then as the temperature reduces, you're forced down into the best choices of solutions. So there's kind of an art to setting up the cooling and deciding when it's done. So you have this kind of monitors that are running as the software runs, and you kind of look at this and say, okay, initially these things hone in on the solutions, so they fall very rapidly, so they move quickly toward pretty good solutions. And as you're in the tail of the solution, you spend a long time to get a slightly better solution. So once you're well out there, the error that you make in stopping the solution a little too soon probably isn't real large relative to all the other variation in these. So that's the current thinking. But knowing when to end these algorithms is an open question in all of these numerical searches. In a lot of the applications you see in data analytics, a commercial vendor may not care if it's exactly the right answer. It just has to be a good one. If you're looking at consumer preferences on movies, you might be getting to 100% of the answer, but it may turn out that 95 or 98 or 99% of the right answer is enough, which sounds a little weird. Do you know what I mean? Because of the fact that you have these underdetermined systems. Yeah.
In writing the software, did you use a particular programming language?
Yeah. So this system, we've gone through an iteration of a number of different languages. The initial version was written in MATLAB, right? It's all matrix-based, so that was the obvious choice. So that was what we started with it. So the one student of mine, John Willis, wrote the first version in MATLAB. So he did I think it was I guess we had external support at the time, so he did it on a kind of a research funding for a summer, and he spent the summer writing the first version of this. At this point, we're using a version that I wrote in R. I wrote it in R in part of just learning how to use R. I said, okay, let's see if I can write this algorithm in R. And so that's the one we're actually using. That turns out to be the fastest one we found so far. I wrote it in Python, and the Python version turned out to run slower than R, which I thought was a little weird. I'd love to have a version of this in C, because that would really scream. Because C is way more efficient than the other languages, and the time is a factor here. So at the moment we're running in R. You can run things in parallel on R, so you can split the problem up, so you can segment problems in R. But the ideal would be to have a segmented program running in C. C is about 10 times faster than R. So, but C is a difficult language to write in. Particularly when we tried to play a lot of games here to try to optimize the runtime on this. The solution that I talked about here, that 600 element solution, takes about 24 hours to produce a solution of runtime. So you start up on your machine, leave it for a day, and come back. Yeah, so it's a long process. Yeah. So there's a lot to be done here in terms of optimizing the performance of these programs. The exciting part is to get it in parallel, because then if you can figure out how to split the problem up and work in individual pieces, then if you could write a good C language program to do the solution, it'll really fly. But even if you can't, right, you just buy more processors. You know, and that these days is cheap. Okay, so.
Are there any further questions? All right, well, thanks.
One more. Oh,
Yeah.
sorry. Yeah.
Curious about how big is your data set?
Well, the one I showed there, the one that took 24 hours to run, was 630 by about 140. The largest one we've looked at was 2,000 by 650. So they're still relatively small, but this is working on segments, you know, of Earth history, right? If we want to go after all of Earth history, we get everything known, right, about it. So eventually, it's going to be a really big problem. So it's not truly big data. It's data analytics. We're not really at big data yet, but we're heading there, right? We're after it. This idea of segmenting problems and working with boundary conditions and things like that are the tools we need. Yeah. So not truly huge data yet, but we're getting there. I could talk about the number of solutions to this. It's a really ugly figure about how many possible solutions there are to this, right? It's a very large number. So yeah, it's NP hard. So nice problem. Okay.
All right, thanks.